Thank you. Thanks for having me, Dan. It's a great pleasure to be here. And I have to say, a lot more snow here in Ann Arbor than I have in Washington, D.C., and I'm not jealous. So I'm going to talk today about Oh My Aching Back. I was going to change the title to be Oh My Aching Back. I can't shovel any more snow, but then I thought I would stay technical and talk about protective aircraft seat design using MR systems. I started working on this a number of years ago. It's interesting, I did a lot of basic research in MR fluids and designs of devices using MR fluids. And then I decided one day to try to do something really useful. And I started jumping into looking at designing seats. And I think we have some pretty good results to share with you. And of course, I don't know how this is going to work here, but I have to acknowledge a lot of people, a lot of sponsors over the years, a lot of collaborators, and a lot of companies have helped support this work. And also my research group, I listed a few of them here that are contributing to this talk, but mostly it's quite a few graduate students and postdocs did all the work, and I get to come here and give the talk. So they do all the credit. So I'll talk today about primarily whole body vibration for pilots. And what's happening is that we're asking pilots of helicopters to fly in seats designed for 2-hour flights to actually fly for 8 hours. And the problem is that they're being asked to do this more frequently, so more flights, the pace of operations is much greater. And also, when you fly a helicopter, you tend to fly in a very asymmetric posture. So you're watching a movie and you're at home, you're sitting nice there, maybe you got a drink in your hand, but if you're in a helicopter, you're kind of like this, you're kind of scrunched over, and you're flying like this for a long time, you're moving the stick. It's a very asymmetric posture. It causes back problems. It causes pain in the legs, pelvis, and pelvic area. Oftentimes, pilots complain of a loss of situational awareness. There's actually been some surveys done. About 33% complain of situational awareness loss because of fatigue from all the vibrations going on, and also 80% complain of back pain. That's a pretty high number. The problem is that pilots won't complain their back hurts, because if they do, they're told you can't fly anymore. Of course, some pilots love to fly, so there's this problem that we have. So the issue here is to solve the problem of whole body vibration in helicopter seats. Now here's a kind of a complicated figure, but it's basically talking about frequency of the vibration that's being imparted to the pilot. Here's the number of accelerations. And you'll see here for different levels, different hours and different so on. You'll see 24 hours here, okay? Get different curves. So here's 24 hours, here's 4 hours. So if you're sitting in a typical helicopter, here's the injurious, this sort of fuchsia color is the injurious vibration level. And if you're flying in that helicopter for around, say, 4 hours, you're going to probably do okay, but you still have a probability of some injury. If you're flying around, say, a very high pace of operations, maybe 2 flights of 8 hours in 2 days, all of a sudden you're looking at this violating virtually every possible scenario for injury. So it ends up being a severe problem. This is actually data from the military talking about probability of injury. So you can see all these curves. You cannot violate these curves, and in fact you do for all these flights. So if you think about a Seahawk helicopter, you've got around 258 rotor RPM. That's around 4 hertz or so. That's 1 per rev. 12.9 hertz is around 4 per rev, and that's like, or 3 per rev, that's actually around your spinal resonance frequency, roughly speaking. That can be uncomfortable. And here's the 4 per rev for a 4-bladed rotor. And that's the major source of vibration. And typically you're talking about somewhere between 0.1 and 0.5 Gs of amplitude of vibration coming to the floor right under the pilot. And this really depends on, of course, the flight envelope and if there's any rotor imbalance or whatever, but it's a pretty severe vibration to be sitting through for 8 hours. Now, the other problem is that these seats that are built, they're really excellent seats to protect your back if you have a impact that imparts a load, say, of 14.5 Gs. That's a lot of Gs, right? Below 14.5 Gs, this seat does not move. It's like a rock, okay? The only thing that's soft here is this nice little cushion there. Get a little pillow to sit on, but that's it. This seat is actually designed to stroke, and you actually have this vertical guide tube here, and these circular pieces here actually slide up and down on this vertical stroking tube here. And this only happens when the load hits 14.5 Gs. This inversion tube will pull out, and the seat will slide down. It'll protect your back. So if you have a 30 G crash, or say a 40 G crash, your back will only see 14.5 Gs. So that's a good thing. It's a very crash-worthy seat. But for small level vibrations, you don't have any protection at all in this particular seat. So suppose you add a damper to this. So we figure some way to add damping. And here's a typical single degree of freedom isolator. Here's your mass and here's your stiffness. And if you had a typical frequency response, you'd see that typical resonant peak. I'm sure you've all seen this in many, many classes, right? And the problem here is that this floor vibrates. Like this is the floor of the helicopter, and here's you sitting in the seat. And you add this damper into it, and yeah, you can knock down resonance, okay? But at high frequency transmissibility, it kind of increases. And so you have this loss of performance. You don't get the advantage of roll-off that you would get in a case where you have no damping. So damping here actually harms you, in a sense. It ruins your performance. You can knock down this resonant peak, but then the problem is at high frequency, you increase transmissibility. Well, how do you solve that problem? That's a sort of topic of my talk. This is a classical trade-off that we see in all our vibrations classes. And so the solution that I'm going to propose today is to use MR fluids in a damper like this, where you have the ability to turn damping on, turn damping off. So in this region here below crossover, you would turn damping on to mitigate the effects of resonance. But at high frequency, above this cutoff, above this corner frequency, you just turn damping off and follow this off-state curve. So you go something like this as opposed to something like that, okay? And so I'll talk about a number of topics here, MR fluids, MR dampers. I'll talk about the Seahawk seat, then a few other topics, and we'll just dive right into it here. So adaptive energy absorption basically is to dissipate energy in vehicle systems to protect occupants or payloads from injurious vibration, repetitive shock, crash, and blast loads. And we've done all of these. I'll only talk today about injurious vibration loads in a Seahawk seat or a Blackhawk seat. But so to do that, I'm going to use MR fluids. So first I'll talk about MR fluids, kind of what they are. And I think I just click on this guy. Okay, so in the absence of field, or in the presence of field, you'll see the material behaves very much like a solid. Okay, so all the particles that are mixed in, these are iron particles mixed into the fluid. And when you remove that magnetic field, the fluid flows like a Newtonian fluid. So in the presence of field, you have essentially a solid, and the solid is not, it's not a very strong solid, only about 100 kilopascals at best of yield stress. But also you have about 1 Tesla of field to activate it, and that's typically quite high, maybe around 0.6 Tesla is typical saturation. And here's a recipe: 1 cup of oil, 1/2 cup of carbonyl iron powder, and you have MR fluid. And there's a few things you have to add to this to make it an effective material. But what happens here is that you'll see all these particles are floating around in this fluid here, and in the absence of field, they just float around. If you apply a stress to that top plate will move, okay, with zero force. Well, if you apply magnetic field, you have a north pole on top, a south pole on the bottom, all these particles that have natural occurring dipoles, magnetic dipoles all line up, they form these chains, and then to get this top plate to move, you have to apply a stress that's greater than the yield stress of this chain. And that gives you the whole mechanism for doing the control and for doing all of the controllable stroking load and shock absorbers and what have you. This is a real phenomenon. This is actually an optical micrograph of a set of particle chains that were formed in a fluid that has partially microparticles and partially nanoparticles. It's a very lightly loaded fluid, about a few percent. So we can show these chains quite clearly. But you can see there's a real chain formations. They actually occur in these MR fluids. This is the mechanism behind how these fluids work. And you can do all kinds of things with MR fluids. Here I show an example of one area where we put in larger particles, nanofibers, and some little smaller particles. We've looked at all kinds of things like what's the impact of particle size, particle shape, volume fraction, viscosity, and so on of the various constituent materials that you use for carrier fluids. Looked at things like elastic percolation and all kinds of things. So it's a very rich field in terms of even material science. So what actually happens here? You take these fluids and you put them into a rheometer and you measure shear stress versus shear rate. And this is typically what you do for a fluid of any kind. Newtonian fluid, of course, the shear stress is proportional to the shear rate through the viscosity. In this case, you'll see that that isn't the case. In fact, you have this high viscosity material that shear thins very quickly to a fairly constant high shear rate viscosity. And this level to which it turns over, is if you take this high shear rate asymptote, bring it back to the shear stress axis, this value gives you the yield stress, okay? And that's an idealization, but it's very useful for design of various devices. You don't operate any kind of energy absorbers or dampers or clutches at these very low shear rates. You're typically operating them at very high shear rates. So here I'm showing data from 0 to 1,000 per second, but in reality we operate from 0 to say 50,000 per second. So this data, if you use that idealization, it works pretty well. So you can express the whole constitutive law here. So here's Newtonian fluid where shear stress is proportional to the shear rate through viscosity. And for an MR fluid, all you have to do is add in this yield stress. You can add it in simply as a bingham plastic characteristic like this, where the shear stress is not proportional to shear rate again, but then we have to add in this field controllable yield stress. And we control that yield stress by applying field through an electromagnet. So I'm talking about dampers. So let's apply this to a damper. So basically we've learned so far that MR fluids exhibit shear thinning and high shear rates. That's that turning over of the curve. Yield stress changes as a function of magnetic field. That's our controllable variable that we're going to use. Our MR fluid behaves approximately as a bingham plastic. And I'm going to talk a little bit now about non-dimensional plug fixes and how you can characterize sort of what's going on in a damper. So here's a typical shock absorber. This is actually a Penske racing car shock that we modified to put in an electromagnet in the piston as well as MR fluid. So when this piston travels through this reservoir of fluid, the fluid passes back through here, past the electromagnet, and in these two regions right here, the magnetic field lines are perpendicular to the flow, and the particles form chains. And then what you have is the resistance to motion of the piston. So you can see here, here's the magnetic coil, and then here's the magnetic field line. So in these two regions right here, you have these chain formations, and there the fluid is like a solid, so it's a very highly viscous fluid. And you get an increase in the force, a stroking load of this device. Now within this device, you have some typical characteristics. You have back here a gas reservoir. You usually pressurize the fluid to keep the bulk modulus as high as possible to get rid of any entrained air, get rid of compressibility in the device. And typically this is a floating piston, or it could be a membrane of some kind. It goes there to create that high pressure. It's also used for when the shaft moves into the reservoir, that change of volume can be compensated for by the change in volume of this gas accumulator. That's a typical design of any myriad number of MR devices that are linear stroke devices. Then you put these into testing machines, of course, and you measure force and displacement and velocity. Here's a typical, this is actually a shock absorber dynamometer. It's one of my first machines I got when I became a new professor. Gary Anderson from ARO gave me $25,000 and said, go buy a machine, and this is what I've got. And so I still keep that in the lab. I don't use it anymore because it's not very helpful for a lot of things now, but I still keep it. And it measures things like this. So what I do is I look at force versus displacement for a sinusoidal excitation of the shock absorber. And in the absence of field, you get a curve like this, okay? And we all know from freshman physics that work is force times displacement. So the area inside of this curve represents the work done on the MR damper, the amount of energy the damper absorbs. If you increase magnetic field, then the area actually increases dramatically like this. And so you get a large change in energy absorbed for a very small change of energy that you put into the electromagnet. It's typically about 20 to 1. 20 times more energy is absorbed than energy you put into the electromagnet. And you'll see on this side also force versus velocity, something very reminiscent of the shear stress versus shear rate characteristic, where again at high shear rates you have an almost linear characteristic. It drops down quickly. And this high frequency asymptote projected back to the force axis gives you like a yield force that you can use to control any particular vibration or shock measurement. The physics of this are quite simple. This is a simple model of quasi flow through a rectangular duct. And it's quasi-static, so there's nothing too fancy. It's incompressible, laminar. And what happens here is you have essentially, you apply magnetic field across this duct. You have a region where the yield stress is greater than the local stress. And so that material right there is actually solid. And then close to the wall where you have the higher stresses is where there's a fluid material, okay? And here's the formula of non-dimensional plug thickness. And what this says is that the plug thickness is proportional to the yield stress and also inversely proportional to the applied pressure, or the load being applied to the device. And what you find is that tau y can be increased, and then you can increase this plug thickness to fully fill in the entire valve, which means you've closed off all flow. It's a rigid link, all right? Or if you did that, but then you increase the load, you'd end up reducing this plug thickness again. If you put enough load, you're going to have zero plug thickness or no restriction in the flow. So it's a pressure-dependent valve. No moving parts, but it's very much like a good analogy is as a mechanical valve. In this case, what I'm showing you here is a ratio. This is C0. This is the force or damping ratio, if you will, at zero field, the absence of magnetic field. And CEQ is the same quantity, but in the presence of magnetic field. And turns out that if you plot this versus non-dimensional plug thickness, so here if you have no plug, there's no restriction in the flow, right? So the field dependent is the same as the off state, so there's no enhancement, if you will, of the damping in the system. But as you increase the plug thickness, you'll see this curve starts to climb dramatically, okay? Until you get to at a one plug thickness, you're going to get infinite ratio. It's a very simple formula. This ratio depends only on the plug thickness. So it's very much like opening and closing a valve. And this curve here, what I'm showing here is I actually put in leakage into the piston because I don't want to have essentially a rigid member here. I want to have something that's continuously flexing. So I put in a little bit of leakage. So there's a finite damping level at when the plug thickness is approximately the maximum level. So there's some, although the MR part closes off, in the piston they put a little simple, say a needle valve or something, to allow the piston to move. Okay, so here I have a similar device. It's a little bit smaller. This is actually an isolator system. I've replaced that floating piston with a membrane, and I now have a spring and a damper in here. And here, I hope you can see this, is a little isolation experiment. And you'll see here that it's vibrating quite a bit and at resonance, okay? And if I turn on the field, it'll knock that vibration down quite a bit. So you'll see the top plate there. It's slowed down in terms of its vibration level. then it increases again, and then it drops again, okay? And so, since we like to look at data, I'll show you a frequency response chart. On this side, this is the uncontrolled case, or this is the case where there's constant field applied. That's like putting in a regular old damper, a passive damper, okay? And you'll see with that damper, here's the original resonant frequency response. If I apply field to this, I can knock that resonance down so I have a transmissibility 1. That's about as good as I can do, right? But at high frequency, I actually get a large increase in transmissibility. But if I use the ability to turn the MR damper off, at this cutoff, or this corner frequency, I can actually drop that down, and I get a much better performance. I can get rid of all that extra transmissibility here by using a simple thing called skyhook control. And all this does is essentially, it's a form of velocity feedback. That essentially, when you get above the corner frequency here, you recognize that the mass and the floor are in a phase, and a simple controller, you can knock this down. You'll notice it's not perfect. I can't get this red curve to follow directly on the black curve because there is some damping in the system, some minimal amount of damping that you can't get rid of. And so, but you get much better performance than you would get here in this case. And that's typically what you're trying to do with these kinds of systems, is get that extra bit of performance. So let's talk about the Seahawk seat and how we apply this in the Seahawk seat. Now, all the projects I showed you before were me working with a graduate student, and the issue here really is I'm trying to really illustrate here the value of industry university teams. And there are many projects you can do where you just can't do it by yourself as a professor in university. You need to have other stuff to use, other pieces. So in this particular project, the Seahawk seat, BAE Systems actually makes the seat. Navair owns the helicopter. I got to use that. And Lord actually has all the MR fluids and other stuff that I need. So it's a very large team of people, along with a group of my former students. I started a company up in Beltsville, Maryland, and they're now called Innovital Systems. And so again, to do this all by myself would be possibly feasible, but you got a team with all the right ingredients, you can make good progress very quickly. So again, I'm just going to focus on this particular seat right here. Here's the same seat I showed you earlier. This is the Seahawk seat. You've got this nice cushion here, the inversion tube, energy absorber. And this is the one that we want to modify to introduce some vibration isolation capability. Again, here's the same cartoon showing the same pain, in the posterior region that comes about from sitting in these long duration flights. And I've already covered that, so I'll skip over that slide. But then, what did I do here to fix the seat? Well, in essence, the seat right now, in previous incarnation, is a rigid seat until you hit 14.5 Gs. So what we decided to do was to take this connection to the energy absorber right here and break it right there, and then float that connection on this cap. And this cap sits on top of this vertical tube, so this cap can actually float up there. It's no longer connected rigidly. The same thing is true over here. We just cut the connection here and attach this to a floating cap. And then inside this vertical tube, we install a spring, an MR damper, and the spring, we drop the resonant frequency down as low as possible, where we still have good static displacement. And then we use the MR damper to do the control of the vibration. So we had to add a couple of things. We had to add this bar right here that prevents the motion of these caps, these floating caps. We want them to stay constant relative to each other, same width apart. We added a control box, and we added another sensor box. So we added a few pounds to the seat, and the seat only weighs about 25 kilograms. It's a very lightweight seat. And here's the final product that we actually sold back to the Navy. There's two versions of them. You'll see why I built two in a little bit. And here's those inversion tube energy absorbers. Here are these vertical caps. It's on top of these vertical tubes. And here's that cross beam right there to prevent swaying or rocking of the caps. and the dampers are inside, you can't see them. I do have some drawings of that. You can see here's the vertical tube here, and then inside that tube you can see there's a spring, essentially, and a damper like this. I'm pulling MR fluid, and these are all the parts associated with that damper. There aren't many. You've got a hydraulic cylinder, end cap, some seals, and here's the piston with the magnetic coil inside. And of course, you have to have leads coming out that go to a power supply so you can control the damping in the device. And that's it. There's no moving parts, no valves, nothing that can break. And so we take that system and then we put it into this. This is actually a big shake table, essentially, for vertical motion. There's a big actuator down below. There's a raft here, and the seat sits on top, and we vibrate the seat up and down. And essentially, we use the frequency spectrum I showed you before, around 0.2 to 0.5 Gs, up to around 20 hertz, and we apply control to see how well this will do in terms of eliminating the potential for vertical vibration. So in this seat, we put in an accelerometer in the seat pan. That's typically where you measure vibrations. We put one on the front of the seat pan, and the problem here, of course, is that your CG of your occupant sits ahead of the vertical bar here, and so you get a rocking mode. This seat rocks up and down, okay? And then, of course, we put an accelerometer down on the floor. So we're going to compare most of what happens between this particular accelerometer and that one, but also this one here and that one there. So the hope is that if we don't vibrate the seat up and down too much, maybe we can eliminate some of the seat rocking mode, okay, without putting an actual actuator in there to control that part. So there's two actual modes here, a vertical mode and a seat rocking mode. So here's the actual result. And you'll see here that this is the OEM seat before we actually put in the isolation system. So we put in the dummy mass and did the measurements. You'll see this green line out here is 4 per rev, and this is 1 per rev. This is the rotor RPM, this is the blade, number of blades, times the RPM. And you'll see here, this is the seat before isolation was put in there, and you get quite a large vibration in both these locations. You soften the seat, you get this curve right here, which you typically do for vibration isolation. And then we add the MR damper in here. And as you do this, when you turn off damping above crossover, this falls back down on the blue curve, which is the case with no damping in it. And you're getting pretty good performance, right? So you're getting results that are kind of what you expect to see. You get a large reduction in transmissibility, but also you're getting very good performance at high frequency. You're getting this large reduction. Remember, this is where all the vibration of the helicopter typically comes in, around 4 per rev. So we have other generations of seats where we've been able to improve this quite a bit. This flattens out some more and comes down even further. And we've done this for a couple of other seats as well. So we're getting, I think, pretty good results. So here's actually the video that kind of shows what's going on here. So here we have controller on, controller off. So imagine you're flying around in a helicopter for 8 hours. What seat would you prefer to sit in? Probably this one here, right? And that's got the MR control in it. So it's not a complete elimination of it because it's almost impossible to do, but it's a large reduction. And so I'm going to show you another video here to kind of uh-oh. Oh. Okay, so I'm going to set this up first. This is a bottle, an Nalgene bottle full of red wine, really old, bad red wine, so we didn't waste everything. And this is the floor of the helicopter, right? And this is kind of what your eyeballs are going to be doing. You're flying around the helicopter 8 hours. These are your eyeballs, and this is the floor, okay? So watch what happens here, and tell me if you think you prefer to have the one on the left or one on the right. So with no control system, you would have your eyeballs doing this for 8 hours. And with the control system, you have this, right? And that's what I'm talking about. The loss of situational awareness that occurs, their eyeballs hopping around like maniacs, is really a severe problem. Okay, so what does all this mean? Well, you look at total reduction of the floor vibration to different populations of occupant. So a 5th female to say a 95th male, you're getting around 90% reduction in the vertical vibration at 4 per rev, which is pretty huge. And compared to the unmodified seat, you're still getting very large reductions in the 4 per rev, anywhere from 82 to 90%, but also for seat rocking mode, you're getting about 73 to 80% reduction. So these are both very large and significant modifications over the seat that didn't have the isolation system. But this is not the final say here, because remember, this is a crash-worthy crew seat, right? It's supposed to be good at 14.5 Gs. It protects your back in a 30 to 40 G crash, right? I just messed around with the seat. I changed it. So I have to go back and certify that it still works in crash. So even though I've modified this, so here I've got a couple different sled tests I'm going to show you. Here's one. The seat sits on its back, and we put in essentially a 46G, 50 millisecond duration pulse. And if you watch this, you'll see the seat start to stroke. See the seat, you can see the back of this frame here. That's the seat actually stroking and protecting the dummy's back from injury. And it turned out by putting in these little simple dampers, now what happens in the original seat is that it will not move until you hit 14.5 Gs. In our seat, it'll move a little bit, just a few millimeters, okay, way before 14.5 Gs. And so what ends up happening is you reduce these peak loads in the lumbar spine by 700 pounds by putting in some very simple little dampers. So we're able to preserve crashworthiness, but also reduce the spinal load by a large amount. Whoops. And then here's the same seat kind of showing from the side what happens. You can see the caps right here. They land on the vertical tubes, and then the extrusion or the inversion tube energy absorbers take over, the seat slides, and you protect the spine of the occupant. So we preserved crashworthiness, we've improved vibration isolation, and what about injuries? Well, there's a lot of things going on in this chart. I'm not going to talk about all of them, but the main thing is peak lumbar load. Here's typical injury tolerances. 2,065 pounds is a typical very fit naval aviator weighing about 200 pounds. And we got 1,250 pounds. So we're way below that injury threshold. Okay, that's a huge benefit. These other ones here aren't nearly so critical to this particular study, but we report them anyway. Okay, so then the test of this is to go fly the seat. Before you can fly the seat in a helicopter, you have to certify certain things. Number one, if you have a crash looking like this, where you have a sort of a sideways motion, this particular angle and attitude, the seat won't fall apart. It has to stay in one piece. This is a very severe worst case scenario. And then you have to go ahead and do another one. This is comparable to a helicopter kind of flaring on landing. And you have to show both of these. So the main thing here is that this seat can't fall apart. This is why I built two, by the way. Remember, I built two seats. And you're going to see it very slow motion. And the seat, I've seen this video many times, the seat never breaks. You'll see that it bends, but doesn't break. So that means we passed that test, although one of our seats is now broken. Made me very sad. Now here's the second seat. I ran this test. This is a little bit more benign in the sense that this is the way it's supposed to work. So it's actually in the attitude it's supposed to be when it's actually operational. And again, this worked out fine. So we passed both of these. And so now we're qualified to fly in the SH-60 Seahawk. And so we go ahead and do that. And this happened late last summer and fall. in 2013 in a Black Hawk, and the summer of 2012 in a Seahawk. And you can see here's the cockpit, and here's the two guys are in there. And there were 4 pilots, and we sort of piggybacked onto some various evaluation missions that did about 8 hours of flight time, okay? And most of the evaluation is subjective, but here are the quotes that came out of the operational reports. I kind of like this one. I felt no different flying in the helicopter than sitting at my desk. But that's pretty good, right? I mean, okay. Upon landing, I felt a lot more beat up in the legacy seat. So in the original seat, they got beat up. In our seat, they felt great, which was good. And then during the speed sweeps, I felt like I wasn't even in a helicopter. So all that vibration's gone. Pilots are happy. Now I have to sell them some more seats. So that's kind of where we are right now. Now, so we have this vibration isolation system, a pretty low weight penalty. We preserved crash safety. The control electronics are all integrated into the seat. We got really good performance. We reduced 4 per rev vibration by 90%. We've eliminated, to a great degree, this problematic seat rocking. We did crash tests and sled tests, and everything worked the way it was supposed to. We did a flight test, and the pilot said he felt like he was sitting in his chair at his desk. So that was a good thing. We felt we achieved everything we had to achieve. And of course, you go to a different seat, and they change everything on you. And so there's these things called fleets. You know, they have different numbers like A, B, C, D. This is the MH60S, and completely different isolation system in the back for shock. And we had to build a whole new one for that. And that one also worked. So we had good performance there as well. Okay, some other thoughts about protective seating. A lot of things I talked about just was for vibration, but a lot of other things happen. Things like you're traveling along, say, an amphibious craft like the EFV, and you hit a rogue wave, and all of a sudden, people that sit in the front here, so here's the commander and here's the driver, so you go over a wave, and guess what gets the hardest hit? The front of the vehicle, right? Because all that big torque, wham. And they actually had an accident where the commander and the troop and the driver both got knocked out from a large wave. And so they asked me to come in here and put in a design into the seat to protect these people in these situations. So we designed that seat. They gave me 2 inches of stroke, and we managed to do a pretty good job of around 60% reduction in shock loads. SOCOM boats, these people that go in the SEALs, they ride these things very high speed and very, very high sea states. They're continually banging their knees and their backs, traveling on these, and we designed seats for them to protect their spines in that situation. And also mine blast. So as I go through this, I'm going higher and higher severity of sort of impacts and blast that the lumbar spine might see. So all these are all big problems, and we're working on all of those for various sponsors. And why is that? Well, here's a quick cartoon showing an occupant, and essentially what we're going to do is we're going to crash, put impact into this, and this is going to slide down. We have a certain amount of stroke, and we want to use that entire stroke to mitigate any shock load that comes in. We'd like to always use all the stroke, because the more stroke you use, the less load you can apply, because work is force times displacement. So we want to maximize energy dissipation by utilizing the entire stroke and minimizing the load to protect the spine. And so what does that really mean? Well, you can come up with some simple optimal controllers, and if you use a typical passive hydraulic energy absorber, what you'll get is you'll get one particular case you can design for. Here's a 50th male, where you use the entire stroke and you come to a nice soft landing, no velocity, no stop impact, everything's great. You put in a heavy person into that seat, they're going to have an end-stop impact, and so you injure the spine, potentially. If you're a light person, okay, the load's going to be too high, you're not going to use the entire stroke, which means you could have reduced the load and reduced the potential for injury by using the entire stroke of the vehicle, of the seat. The solution for this is quite simple. It's based on a Schottky diode equation, and there's details in various papers on this I can send if anybody's interested. But the idea is that it's a very simple controller. Again, it's an optimal control technique, And you can apply this in things like automotive seats. And here I have a couple of videos I took when I was working with GM. And you'll see here, I'm just going to run these videos off real quick at the same time so you can kind of see. And you'll see here, the seat starts to stroke, and I have 2 inches of stroke right there. And I can drop loads down from 30-some Gs down to about 10 to 15 Gs. And this is only for low speed, say 15 miles per hour before the airbag deploys. But the point is that you can do quite a bit with a little bit of capability. So what's the kind of the state of the art in sort of MR energy absorbers and MR dampers and so on? Well, typically you're looking at things like maximum field-on force versus maximum piston velocity. And most of the work being done is kind of down in this region right here, fairly low speed, fairly low force. And even things like landing gear problems, you're operating kind of up in this is actually an MD-500 helicopter type landing gear oleo. You can see you're operating way up here. And in some cases, you're operating even up here. And so for some of these blasts and other events, you need to have dampers that can operate out here. The complications are high speed, high shear rates, turbulent flows, all kinds of other issues that come up that you don't see down this region right here. So one of the key problems as well, if you're going to be operating these dampers at high speeds, you're actually operating at high shear rates, you don't have data up there, okay? So one of my PhD students right now is actually working on trying to get data as high as, say, 25,000 per second shear rate. And what you see here is zero field and maximum field. And the issue was, do we actually have any controllability in the yield stress at these high shear rates? Well, in turn, we do. We lose quite a bit, but we still have some good controllability with these high shear rates. First measurement's done at these kind of high speeds. And the other thing you want to look at as well, if you plot normalized apparent viscosity versus Mason number, these are two different non-dimensional groups. Normalized apparent viscosity is the viscosity of a particular shear rate divided by the high shear rate viscosity. And Mason number is like a magnetic stress divided by a viscous stress. If you plot this versus that, all those curves I just showed you should collapse onto a single line. And in fact, they do, even at these high shear rates, except for this one particular case that's making me scratch my head. This is actually a low field case, but I think what we have there is a problem with calibrating our Hall effect sensor to measure magnetic field as opposed to a problem in the physics. So all the other cases fall in the same line. So again, we're able to get good data up at these high shear rates, and so we can sort of envision doing some of these crash tests at very high speeds. And here, again, you can see, even at these high, this is all done at 25,000 per second, you can see we're actually measuring quite significant changes in yield stress from these materials. So we're getting good results. And but the problem is that, as you go faster and faster and faster, you're pushing these particles and these fluids through valves so quickly, will the magnetic field really cause them to chain up and create yield stress anymore? They're not going to be in there long enough to do that. So another big area we're looking at is particle interaction models. And so we're taking particles and we're looking at the interactions of these particles. And what you see is that most people look in the tens to hundreds of particles, and you'll get nice models. You apply magnetic field and you'll see the particles move and they form chains. You can do pretty well, but that's not really enough to do realistic modeling of MR fluids. To get practical simulation volumes, you need something on the order of 1 million particles, something like this is a typical, say, annulus in a valve. And here you're seeing about the volume we can do right now. You're getting essentially about 1 million particles there. And to do this, we're actually using parallel processing using NVIDIA's CUDA compiler on a GPU. And that gives us very, very high speed or highly parallel capability to measure these behaviors. And so I'm just going to jump ahead here. You can see in typical MR fluids that you get these lamellar sheet formations. You'll see there's these chain formations. When you shear the fluid essentially in this direction here, you get these sheets forming. This is an ER fluid, and you can actually see this also in MR fluid. I think we're the first ones to actually simulate this an MR fluid. And over here, I'm going to show you another video of how this actually sort of tunes up here. Whoops, I think I went too far. So you'll see I'm going to spin this around. I'm actually shearing the top plate relative to the bottom plate of this cubic volume here. And what you'll see is as time goes on, you're going to see these sheet formations come about. And here I'm talking, hundreds of thousands of particles in this particular case. And if you look at this, you can see I'm shearing on the top plate in this direction. You'll see the shear angle's about like this. You kind of squint a little bit. And then when you come back around, you'll see again these chain formations or these sheet formations come up. And that'll stop right when you get probably the best view of these sheet formations. So we're able to simulate, you see the sheet formations here, simulate large numbers of particles in these kind of situations. And now we're looking at putting them into Poiseuille flow in a CFD code. So it's still a very rich field of research. We're doing a lot of work with all kinds of different things, crew seats, blast mitigation, crash protection systems, a lot of work looking at high shear rate flows. I'd like to get about 100,000 per second data. So we have this big 75 horsepower motor that I'm working at as a Rheometer. I'm going to better understand all these different non-dimensional numbers and analyses that are used to characterize MR fluids. Typically we're using things like Mason number, Bingham number, and Reynolds number. And so understanding that and modeling is a good thing to look at too. And also design better devices, lighter, higher bandwidth in the works. So some final thoughts. These are all my students. And in fact, this is a wind tunnel that was built by a high school student and who I know very well. And students went and demonstrated this wind tunnel at a Discover Engineering Family Day every year. So go out, serve AAA, engage in outreach. One of my final thoughts. Serve your profession. Convince other people to come into aerospace engineering. Mentor students and colleagues, right? Nominate, nominate, nominate. Create a culture of nomination. A lot of really smart people, right, deserve awards. Nominate them. Here I'm showing, here's one of my former PhD students who got an award. There's another former PhD student who got an award, and here's one of my current PhD students who got an award. And AAA has a wonderful professional recognition program. Partake of it. Do these things. Nominate people for awards and show your appreciation. Go to new countries and try on some new clothes. So you'll see here, I'm dressed up as the King of Korea, and I'm not sure who this young woman's name is. She was the Queen of Korea, but we're not related. So, yeah. And then here's another one. Take your students with you, take your postdocs with you, go on great trips and go to conferences and learn some stuff. And also go visit some interesting sites. That's always fun. Take your family with you. I went to Bangalore a few years back and brought my family. We had a great trip and got caught in a rainstorm here, but it was one of the temples in Bangalore. And life is full of great times. Enjoy them. There's a picture of my wife and my daughter in Paris, and my second daughter, Chani, she's actually at Miss Saigon in Strathmore in Rockville, Maryland, singing. And I wouldn't have missed that for the world. So, very proud of both my daughters, and they do great things. Don't miss those things. Go home for dinner. And I'll take any questions.